Hi, this is the second lesson for Unit 5, and in class we started talking about what proving trig identities was, and we went through some tips for proving trig identities. The idea, as we discussed in class, is that we want to try to show that one side of the equation is equivalent to the other side. And generally speaking, we want to start with the side that is more complex and simplify it until it matches the more simple side. In this case, the left-hand side is the more complex, so we will start with that. We'll indicate on our paper somehow that that is the side that we're starting with. And here I'm going to choose to take out the sine of theta as a factored out term, and then I will be left with this. So my first step is to identify the side, and I can do that by recopying it or by somehow indicating that this is the side I'm beginning with. And then I'm showing the factoring. Once I've factored that out, I want to think about my different trig identities and think about what 1 plus cotangent might be equal to. And if you look at your trig identity sheet, you'll see that 1 plus cotangent squared is cosecant squared. So in my next step, I'm going to show keeping the sign, and then this part that's in parentheses is equivalent to cosecant squared. So someone following my work could see I didn't change this, but I did change that. Now I'm going to do one more step. In this step, I'm going to keep the sign still yet again, but I'm going to change my cosecant being 1 over sine. And since the cosecant is squared, so will the sine be squared. And in the next step, I'm going to say, well, this sign is going to cancel one of these. So I could show that in the line above just to help. So I'm not going to scratch it out so much that I can't see what was written there before. And I can show that that is now 1 over sine. And then I should know that 1 over sine is equal to something. What is it equal to? It's cosecant. That's one of the reciprocal identities. So I look back at the original question if I can get my computer to cooperate with me, and I notice that that is what I was trying to prove, and I did in fact get from this beginning side to saying cosecant. So now the problem is done. Next example. Tricky thing here might be deciding what to begin with, and after some thought and some experience, you'll have an idea that maybe you should start with the left side. So I'm going to show, I'm actually just going to rewrite the left side because I think that's a nice way to show which side I'm beginning with. And then I'm going to say, well, there's too many different functions here. So I'm going to keep the sine and the cosine. I'm going to write tangent as sine divided by cosine. And the reason that I might do that is because that was one of my tips, right? That it could just switch everything to sine and cosine. Sometimes some stuff will cancel out like that. Cosine top and bottom makes a 1. And now I have sine times itself, and sine times itself could be written as sine squared. And if I think about those Pythagorean identities, one of the Pythagorean identities has sine squared in it. And if you rearrange that Pythagorean identity for to have sine squared alone, that's equal to 1 minus cosine squared. That's by an identity, using the Pythagorean identity there. Third example. This one is pretty tricky as well. But I think on this one I'm going to again start with the left side. And then I'm going to use that idea of writing things in terms of sine and cosine. Tangent is sine over cosine. Cotangent is is tangent's reciprocal. So cosine is on the top for this, and sine is on the bottom. And then this looks like a big bunch of gobbledygook, and it's going to look worse before it looks better. We're going to find a common denominator. So we're going to multiply this one. I'm just going to abbreviate here for the sake of space. I'm going to multiply by sine over sine, and here I'm going to multiply by cosine over cosine. It is not standard to write just a CR and S. I'm really just doing that because I didn't plan ahead and I didn't leave myself space on the left there. This result will be sine squared over sine times cosine. That's the first fraction. The second fraction will have cosine squared on the top. And again, we'll have sine and cosine on the bottom. Now, the reason I would want to do this is because now I have a common denominator. And the common denominator is sine and cosine. Okay, I do not know why the computer's doing this. Hold up. Okay, so because we have a common denominator of sine times cosine, we can just combine the two fractions. So this is showing here the combining of the two fractions. And now on the top, hopefully you recognize that this part is a Pythagorean identity. What is sine squared plus cosine squared equal to? Equal to 1. So I've got 1 over sine times cosine. And I could think of that as being two separate fractions. The two fractions would be 1 over sine, 1 over cosine. And what's 1 over sine equal to? Cosecant. And 1 over cosine is secant. So now if we go back, that is what we wanted on this side. That's a pretty long problem, especially with this crazy thing in the middle. Look at this. What in the heck is that? That's crazy. I don't know what the pen is doing. Hi. Okay, the last one is very, very tricky. So I guess I've spoken about every problem. They all are kind of tricky. I'm going to start with the left side, which looks like this when you write it with this horizontal fraction bar. I want it to equal this fraction at the end. What I'm going to do is a strategy that is called multiplying by the conjugate. And so even though I can't treat this like an equation I'm solving for and multiply both sides by something, I can multiply by anything that's equivalent to 1. And the reason that this is helpful is going to be clear in about a step to 2 steps. I'm just going to rewrite the numerator now. I'm just multiplying the fractions by going straight across top and bottom. And then here I'd have 1 minus cosine and 1 plus cosine. If you remember when we were talking about factoring patterns the other day, there's a name given to this factoring pattern that you have on the bottom. It's called a difference of squares. But it's already in factor form. What I'm going to do now is make it multiply together. Use FOIL. So if you multiply the first term times the first term, you get 1. Outer terms would give you plus cosine. Inner terms are going to give you minus cosine. So those cancel out. And then I have minus cosine squared. This denominator is like trig magic because it's an identity. It's related to an identity. That bottom part is one of the Pythagorean identities. 1 minus cosine squared is sine squared. And then the top I'm going to leave just as it is. And then there's some magic canceling that can happen. This sign will cancel one of those signs. And in my last step here, I have 1 plus cosine on the top and just a single sign on the bottom. And that was the right side of the equation. So thank you so much for watching those 4 examples. Please watch any parts of them again that you're confused about. If you're confused, for example, about how I got from here to here, that was FOIL, multiplying binomials together. Go back and take a look at that again if you need to. It's a problem like this, right? And then you just multiply the bits together. Okay? That's what I was doing in that step. But for anything like that where you're a little bit unsure, that's an advantage of video, is that you can watch it again. I'll see you in class. Thanks.